Okay, hi, we're back for Module 19. We are on Unit 3 of Populations, and in our textbook, we are in Chapter 6, Module 19. And we're going to talk a little bit about population growth models. Now, we've had some experience with this with some of our labs and some of the assignments that I've given you. So this will be reinforcement for that. So, why do we need population growth models? Well, scientists use models to help explain and predict changes in an environment, right? So, population growth models are actually mathematical equations that help us to predict population size at any moment in time. And the reason that yes, it helps explain and predict changes, but why? So we can protect the environments if we see that there's a danger. We can manage something and we can control it if it's invasive. So it's very good. Population growth models are really helpful for us. Okay, so there's two of them. There's exponential growth and logistical growth. And we're going to talk about the two different ones, okay? And there's some terms that you need to understand in here. But exponential growth model, here's the formula. You're not really going to have to solve it like this particularly, but let me tell you what it means. It estimates future population size, which is n, after a period of time t, based on growth rate r, and the number of reproducing individuals currently in the population, which is the NO. This is always presented as a J curve. Okay, and this is what the J curve looks like right here. Whoops, right here. It's the exponential growth model. When populations are not limited by resources, their growth can be very rapid. There are more births that occur with each step in time, creating a J-shaped growth curve. So what kinds of factors do we find in the environment for exponential growth? We find abundant food, high reproduction and high survival, low death rate. Okay, we have to take into account the intrinsic growth rate, and the analogy that they give here, if you're interested, is a bank account accruing interest. Okay, and then the next model, and just to make sure we understand, it's not limited by resources. This particular one, there's rapid. The growth is rapid because more births occur with each step. So it's like if you put money in the bank, you get interest. If you put more money in the bank, you get more interest, and all of that accrues. And the same thing with the exponential growth model, but it produces a J-shaped curve. It starts out very slow, but as there's more, it actually comes up very high. So it starts out small, and then as that interest, quote unquote, accrues, there's more, and then more, and then more, but it exponentially grows. Okay, so the logistic growth model, on the other hand, describes populations that experience a carrying capacity. And remember what we said about carrying capacity. So a logistic growth model is a model that describes a population whose growth is initially exponential, just like this, but it slows as it reaches the carrying capacity. And in this model, you're going to see an S-shaped curve, and it will top out at the carrying capacity. Remember, the carrying capacity is the capacity for that environment to handle that particular population. And this is more about density dependent factors. And of course, you can read more about this over here. But that's it. Okay, let me show you the curve. Here's the S curve. So there's early growth exponential. You see it starts out very slow, and then interest is accrued, or over time there's more population, and there's more reproduction, and lower death rates, and it exponentially grows. Then the growth begins to slow, but then as it reaches the carrying capacity, it falls to zero. Sometimes species will overshoot their carrying capacity, and this is the word overshoot, and it literally means when a population becomes larger than its carrying capacity. So it's larger than the resources available for its survival. So if that was the Serengeti, it would mean the animals didn't have any more grass, that they ate all the grass. There was too many of them, and there's no grass left. So they would move, obviously, but that particular environment they wouldn't be able to survive in. So if a species reaches and exceeds its carrying capacity, what happens is something called that's overshoot. And then it leads to something called die-off. And so die-off is a rapid decline in the population due to death. So you can see it hits the carrying capacity and a rapid decline. And this is the case with the St. Paul Island, Alaska reindeer population. Humans introduced 25 reindeer to St. Paul Island in 1910. Population initially experienced rapid growth that approximated a J-shaped exponential growth curve. But in 1938, the population began to crash because the animals exhausted their food supply. Okay. There's something else that's called oscillations. So when a population overshoots its carrying capacity and then has a die-off and falls below its carrying capacity, sometimes there's cycles of overshoots and die-offs, and they lead to this pattern called an oscillation, a population oscillation. That means that it's going up and down, up and down. And then eventually it levels off at the carrying capacity. It can't sustain anything more than that carrying capacity. So it will eventually level off that way. So here's 2 case studies here. I would like you to read these and in your own mind try to interpret them. But this is population oscillation. So now you know what that means. They overshot their carrying capacity and died off. Overshot and died off. So both lynx and hares exhibit repeated oscillations of abundance, with the lynx population peaking 1 to 2 years after the hare population. So you could see that, right? So when the hares are not abundant, there's plenty of food, which allows the hare population to increase. But as the hare population increases, there are more hares for lynx to eat, so the lynx population increases. So as the hare population becomes abundant, they start to run out of food, and then the hare population dies off. As hares become less abundant, the lynx population dies off. And with less predation and more food, once again, the hare population increases again, and the cycle keeps repeating. Okay, so you might want to take a few minutes for yourself to really look at the graph that's presented here and try to figure out which line is which and what are the numbers of hares versus the numbers of lynxes, what's on the X and Y axes, what are they showing. Please try to spend a few minutes to analyze these 2 graphs. I'm not going to go through this one. Okay, so the next section is species have different reproductive strategies. Okay, so obviously the way that populations increase is through reproduction, right? So population ecologists have identified a range of reproductive strategies in nature. And I'm saying a range because we're going to talk about 2 of them. We're going to talk about a K-selected species and an R-selected species. But as you know, if you watch the video, there's sort of like a continuum in between. They don't all fall into one or the other of these categories. But the K-selected species are species that have low intrinsic growth rate. It causes that population to increase slowly until it reaches carrying capacity, right? And they have a long, here I've written it here for you. I've written some, I didn't put it over here because there wasn't room. But the K-selected species, these are the traits. Now you need to know these for the AP exam. These things are going to be asked on the AP exam. You will be asked to answer questions based on some of these traits. So please write them out here. I know you're probably saying, well, it's in the textbook, but just write it out because when we go to review, these are going to be your review notes. K-selected species traits, they have a long lifespan. They have long time to reproductive maturity. So in other words, they don't have offspring early in their lives. It takes a longer time to reach maturity. To reproduce. They have fewer reproductive events. That means they're not reproducing that often. They have fewer offspring when they do reproduce. They have large offspring. They have parental care, which means that the parents have to take the time to raise the offspring. They have slow growth, intrinsic growth, and they're density dependent. And that means they rely upon the resources within the environment. And then their dynamics, their population dynamics is pretty stable. There's births, there's deaths, there's migrations, there's emigrations and immigrations, but really it evens out. So there's a stable population dynamic. The R selected species traits are completely different. So they have a very short lifespan. Should we say an example would be maybe like an elephant or a human being would be a K selected species. Okay, our selected species traits are short lifespan, short time to reproductive maturity, many reproductive events, many offspring, small offspring, no parental care, so the parents don't have to worry about taking care of them, so they can go on to have other other offspring. Fast growth rate, density independent, highly variable population dynamics, and they are prone to overshoots and die-offs much more than a K-selected species would be. So, you might think of like a mosquito for this one. Okay, so, and there's a little chart here too if you want. Okay, so survivorship, you might be asked to compare and contrast this on the AP exam. That's why I want you to make sure to write these notes. Survivorship curves are patterns of survival over the lifespan of individuals. And you've seen the charts already on the videos, and if you haven't, you will be seeing them soon. There's 3 types. There's type 1, type 2, and type 3 survivorship curves. And curve is exactly what it means. It's a curve on a graph. Okay, so the type 1 curve has high survival throughout most of its lifespan and dies in large numbers as they approach old age, which obviously sounds like humans, right? And type 3 has low survivorship early in life, few reaching adulthood. You could think of dandelions maybe for that. And then in between, because remember I said there's a continuum of these. In between we have the type 2, which is constant decline throughout their lifespan. Corals and squirrels and birds sometimes are considered that. So here we go. Here's the survivorship curve graph, and so it shows you here. Here's the dandelions, right? So type 1 would be like humans, right, or elephants, or whales. So we have survivorship throughout early life, and then it tanks at old age. And then we have the squirrels who's, in the middle, and then we have the dandelion that die off very quickly. So that's it. And then we're not going to talk about this, so we could skip that section. All right, so that's Module 19. Here's your 4 questions. I'd like you to put your answers here, and I will be checking them. All right, I'll be back for the next one.